Thank you, Daniel. Thank you, everybody in the organizing committee to make this event possible and to invite me to give a contribution in this One World IAMP Mathematical Physics Seminar. So you can see the title, From Short Range to Contact Interactions in Many-Body Quantum Systems. Short contact interactions were conceived in physics as idealizations of very short-range interactions. So you have typically nuclei, for example, in nuclear physics with forces which are very short range, and as an idealization of such very short-range interactions, these contact interactions were conceived. And in 3 dimensions, the first to do this were beta and piles, as far as I know. But so this was always the idea: contact interactions should be limits of short-range interactions, idealizations, simplified idealizations, and therefore they should be really limits in a suitable sense of many-body Schrödinger operators. And in short, that is the message of this talk. Contact interactions should be limits of Schrödinger operators. And the message is, yes, they are limits of Schrödinger operators in a suitable sense. And in which sense they are limits will be seen in the course of this talk. This is fairly recent work, but most of my talk I will spend on explaining to you what contact interactions are. I assume that many in the community are not familiar with contact interactions for many-body quantum systems, because in dimensions 2 and 3, this is a fairly new model, and it still has kind of the flavor of an exotic model. So, but before I begin, I'd like to mention my collaborators, former PhD student Ulrich Linden and Michael Hofacker, who joined me in my research on contact interactions and from whom I learned a lot and I benefited a lot from this collaboration. So here you see some well-known famous models of contact interactions, which probably you all have heard of. The first in the line is the Kronig-Penny model of one electron in a 1D crystal, and the atoms, the potentials of the atoms are modeled by delta potentials in a periodic array. This was in 1931. Then in 1935, Beth and Piles wrote a paper about the binding of the deuteron, which is a 2-body system composed of a proton and a neutron. And they described this in terms of a contact interaction, which they modeled in terms of a boundary condition at the point where these 2 particles meet. And everybody knows the Lieb-Lininger model for 1D Bose gas. And the very recent model is the so-called Fermi-Polaron model, which is a model for free fermions, a number n of free fermions, which are in contact with an impurity particle. And typically, the interaction in this model is chosen as a contact interaction. And this is actually the motivation, or was the main motivation initially when we started to work on contact interactions. So what are now contact interactions? So here is a very general mathematical description. Let's consider a free Hamiltonian H0 describing n non-relativistic quantum particles with masses mi in the Hilbert space H, which is L2 R to the nd. So the particles are moving in d dimensions. For the moment, d is arbitrary. And the masses mi are positive and arbitrary, but for simplicity later on, I will put them equal to 1. But in fact, the masses are really arbitrary. So let gamma be the union of the collision planes gamma I, j. So for each pair ij, we have collision plane, which is the set of points in the configuration space R to the ND, where two particles meet. So this is a ND minus D dimensional hyperplane. Now, by definition, an n-body Hamiltonian with contact interactions is any self-adjoint extension of H0 restricted to C0 infinity functions which vanish on the collision planes. So as long as the wave function vanishes on the collision planes, the energy should be given by the free Hamiltonian H0, but at the collision planes it may deviate. So this means H should be self-adjoint. That's property A. And property B, H should agree with H0 for functions which are in C0 infinity R and D minus the collision planes. And of course, the domain of H should be larger than this space of smooth functions. That's a very general definition, of course, and very likely there are many self-adjoint Hamiltonians satisfying this characterization, but which are not physical because they may be non-translation invariant, non-local, whatever. What we're actually looking for, is some rigorous version of what you see here in the last line, which is a formal expression for a Hamiltonian with contact interaction, where simply you see a sum of delta potentials with some coupling constants mu ij, and that's actually something we are looking for. So this is easy to make rigorous in one dimension, and you may know this is essentially the Lieb-Liniger model, except that the Lieb-Liniger model is usually considered in a box or in a finite length interval, while I now look at n particles on the real line. An important object to define the energy of this Lieb-Liniger model are these trace operators, T, I, J, which you see in the first line, which are operators from H1, the Sobolev space of functions which have one weak derivative, still in L2, and Tij maps to L2 of R to the n minus 1. And the action of this trace operator is simply to put the positions of the j's and the i's particle equal. So Tij psi is basically now a function on the collision plane where the i's and the j's particle meet. It's well known in the theory of Sobolev spaces that this operator exists as a bounded operator from H1 to L2, and on smooth functions, so the second line where you see the definition of Tij, this is something to be considered on smooth functions only. Now, in terms of these trace operators, we can now define the energy of this n-particle system with contact interactions by equation 1, or by the expression 1. We have the kinetic energy. Now all particles have mass 1, the gradient of psi squared, plus the sum of the interaction energies for all pairs I less than j with some coupling constants beta ij. And we integrate here over the collision planes the traces Tij applied to the wave function psi. This is obviously a quadratic form. It's well defined on Sobolev space H1. It is bounded below, one can show, and it's closed, which means that if you add a suitable constant, then it defines a norm which is equivalent to the H1 norm. So by general theorem, such a quadratic form defines a semi-bounded Hamiltonian, which I denote by H beta, and now beta stands for the collection of these multi-indices beta ij. So this is the Lieb-Liniger Hamiltonian, and you have studied this Hamiltonian for one particle or for two particles with center of mass reduced in quantum mechanics 1, and you know that the wave functions in the domain have a jump in the derivative at the place where the particles meet. So this can be derived from the expression for the quadratic form, and there's nothing, there is no surprise, nothing unexpected happening here. But until recently, nobody asked whether this Hamiltonian H beta is in fact a limit of Schrödinger operators, and the first to address these questions were Basti, Cacciaporti, Finco, and Theta, which looked at the n and the 3-particle case. And a little later, we considered the n-particle case, in which we proved that H beta is in fact the norm resolvent limit of the Schrödinger equation, Schrödinger operators that you see in line 2, in equation 2. So we have Schrödinger operators H beta epsilon minus Laplace for the kinetic energy, sum of two-body potentials with some coupling constants beta ij, which are the same beta ij that you see in equation 1. And then we have potentials, two-body potentials, which are rescaled in the way you see in line equation 2, in such a way that since we are in one dimension, the integral of the potential is equal to a constant, which I normalized to 1. This is important. If this integral of the potential were another constant, then the constant, that the coupling constants beta ij in equations 1 and 2 would not agree. So this is the result, and it justifies the Lieb-Linear model as a limit of models with short-range interactions. Now, a few words about the proof. The main ingredient for the proof that you need to know is that the Schrödinger operator H epsilon, I dropped the beta now, can be written in a very simple form. As you see here in the first line, it's minus Laplace minus A epsilon star B epsilon. So this product form is very important because it allows you to compute the resolvent of H epsilon explicitly, as you can see in the following line. And this is what is called Kono-Koruda formula. It's actually due to Kato, but it's a well-known formula, and you can also understand it based on Feshbach-Schur method. And you see here the resolvent as the sum of the free resolvent R naught of Z, that's the resolvent of the Laplacian, plus perturbation. And this perturbation contains 1 over theta Z of Z, which is given below. So you can think of this, if you haven't seen this before, you can think of this as for Neumann expansion. You do the von Neumann expansion of the resolvent of H epsilon. Consider the A star B as a perturbation, and then it turns out that you can resum this von Neumann expansion. And there is a geometric series inside, and this can be resummed, and this leads to the 1 over theta epsilon of Z, which you can see, which is obviously, from the definition of theta epsilon, a sum of a geometric series. So this is the main step. This is the starting point. Of course, the A epsilon and B epsilon have something to do with the square root of the potential. And if the potential has a positive sign, if it doesn't change sign, the B epsilon is equal to A epsilon. And in the case where you have, let's say, only one particle, then this has something to do with the Biermann-Schwinger principle, dB R naught A epsilon, which is in the definition of theta epsilon, is then the Biermann-Schwinger operator. So for this reason, I will call the theta epsilon a generalized Biermann-Schwinger operator. If you know Feshbach-Schur, the Feschbach-Schur method, then you can think of the resolvent of H epsilon, and so you can think of H epsilon and theta epsilon as the first and the second Schur complement of a bigger operator. Now, in the limit epsilon, one can prove that all parts in this formula, in this Kono-Koruda formula, have limits. P epsilon times the resolvent has a limit in norm. 1 over theta epsilon has a limit in norm, and R naught A epsilon star has a limit in norm. And that's the way you arrive at the Lieb linear model in the limit epsilon going to 0. Of course, in the end, you will have to integrate out the potential, which is still somewhere in there. It would be much easier to prove strong resolvent convergence. Now, strong resolvent convergence is convergence of the resolvent applied to some fixed vector. But strong resolvent convergence is a much weaker statement than norm resolvent convergence. Norm resolvent convergence implies convergence of the spectra, while strong resolvent convergence does not imply convergence of the spectrum. The spectrum may collapse. Now, strong resolvent convergence happens to be equivalent to what is called gamma convergence. And gamma convergence, so this gamma has nothing to do with collision planes. The gamma convergence is a notion of convergence for quadratic forms. And so the resolvent of an operator applied to a vector is the solution of a non-homogeneous linear equation for a symmetric operator, for example. And such a non-homogeneous linear equation can be expressed, the solution can be expressed in terms of a minimization problem for an energy form. And you may know this from the Dirichlet problem. So this gives a connection between energy form and the resolvent, and this is what is actually used to see that gamma convergence is equivalent to strong resolvent convergence. Anyway, this notion of strong resolvent convergence, or this notion of gamma convergence simplifies a lot the proof of strong resolvent convergence. You don't need this Kono-Koruda formula, then you can work with the quadratic form. An important role, as I mentioned before, are played by these trace operators. You see them on the last line again, which are bounded operators from the Sobolev space HS, Rnd to Hs minus d half. Rnd. So they are trace operators reducing the dimensions, the dimension by d, and therefore the Sobolev index is reduced by d half. And this is a bounded operator as long as s minus d half is positive. Now this happens to be positive when s is 1 and d is 1. But for d 2, 3 or larger, it's not positive anymore for s equals 1. And that's the reason why this approach through this quadratic form works in one dimension, but it does not work in higher dimensions. So contact interactions cannot be defined in this way, in this simple way, in higher dimensions. So in a nutshell, this is the main difference. That's the main source of the problems. So the question arises, are there contact interactions in higher dimensions? And if yes, what are they? How do they look like? So for dimensions t greater or equal to 4, the answer is very simple. There are no contact interactions because in this case, the Hamiltonian H0 is essentially self-adjoint on this space of smooth functions, which means that the only self-adjoint extension is H0 itself. If you look at fermions in dimensions d greater or equal than 2, spin 0 fermions, then there's no contact interaction either. For the same reason, the Hamiltonian is then essentially self-adjoint. The only exception is the case d equals 1, where there is something like delta prime interactions. Delta prime interactions refers to a type of interaction which depends on the slope of the derivative of the wave function where the particles meet. Such an interaction is possible in one dimension. So there is a possibility that particles in one dimension interact through this delta prime interaction in spite of the fact that the wave function vanishes there. So even for fermions, there is this possibility of point interaction. But we will not look at this interaction anymore. In the following, I'm not aware of a physical model which contains these delta prime interactions. So what remains are the dimensions d1, d equals 1, 2, and 3, and n, an arbitrary number of particles. And in fact, in this case, there are infinitely many Hamiltonians with non-trivial contact interactions, I claim. And this follows from Neumann extension theory, because the Hamiltonian H0 restricted to the smooth functions in this case, always I'm talking about smooth functions vanishing on the collision planes. In this case, this Hamiltonian is not essentially self-adjoint. It has the efficiency index, which is in fact infinite when you have more than one particle. And there are consequently infinitely many self-adjoint extensions. In fact, even in the case of one particle with a delta potential at the origin, there are infinitely many self-adjoint extensions, as we will see in a moment. But this follows from Neumann extension theory. So we look now at this case is only dimensions 1, 2, and 3. And we look at the simplest case of two particles with center of mass motion removed, which is the same as a delta potential at the origin. And as I said, dimension is less or equal than 3. And this problem was apparently first considered by Beresin and Fadeev in 1961. So look at equation 3. We look at Laplacian restricted to H2 functions, which vanish at the origin. Now, before I had here smooth functions vanishing at the origin. Now I consider the H2 functions, a little space which is a little bigger. This excludes then the delta prime interaction. I could just as well consider again C0 infinity functions vanishing at the origin, but then I would have the delta prime interaction in addition. In this way, I can say that all self-adjoint extensions of this operator are given by H beta, one parameter family of operators whose resolvents you can see in equation 4. And theta of z is given by expression 5. So you see here the free resolvent again in 4 and a rank 1 perturbation. The Gz is the Green's function of the free Laplacian at the point z, or what you can see below the solution, the fundamental solution of minus Laplace minus c. It's an L2 function. This defines this rank 1 perturbation that you can see in 4. And there is a factor, complex number in front of this rank 1 perturbation given by 5. And this theta of z contains the parameter beta, which measures the strengths of this point interaction. There is the inner product of G lambda and Gz, and lambda minus z in front. And the lambda is a real number, which is simply a given reference point. You can choose lambda equals -1, for example. It should be in the resultant set of the free Laplacian. So this is a very nice expression, this formula 4. You can read off from this expression, for example, the spectrum of H beta. It contains the spectrum of the Laplacian and all the poles of this rank 1 perturbation, which are the zeros of theta of z, are eigenvalues. And there is exactly 1 0, or at most 1 0, because it's a rank 1 perturbation, which gives you then a bound state. You can also read off from the equation 4 the domain by simply applying both sides of this equation to a given fixed vector in the L2 space. And by doing this, you see that the vector psi belongs to the domain of H beta, even though if psi is a sum of two terms. Psi equals u plus gzw, where u is in H2, the domain of the Laplacian, and the gzw, that's a multiple of the Green's function. W is simply a complex number. This is something which is relatively singular compared to the u. It's in L2, but it's not in H2. The u is in H2, the domain of the Laplacian. The gz is not in H2. So that's the way you should think of this. It's a decomposition of the psi into two pieces. One is regular in H2, the other one is singular. Now, the complex number w is not free to choose. It also depends on u, because the way you arrive at this decomposition is by applying 4 to some fixed vector phi. And in this way, you see that these two contributions, u and gzw, actually are dependent. And this equation u of 0 equals theta z times w expresses this dependence. So that's important for all that is to follow, that you have some kind of boundary condition. And in this simple case of a delta potential, you have this boundary condition at the point x equals 0, which you see here. Now for the following, to understand the following, we adopt a new point of view. That's below this horizontal line in equation 6 and 7. So we introduce an operator t. By t, u equals u at the origin. It's well defined on H2 RD for dimensions t less or equal than 3. And you can formally see this as the inner product of the delta potential, or the delta function with u. So this is simply the delta distribution applied to u. So with this notation t, we can now say that H beta in line 6, equation 6, is a self-adjoint extension of minus Laplace restricted to the kernel of t, right? The kernel of t is the set of functions vanishing at the origin, and that's exactly what we did in equation 3. So equation 6 now is the same as equation 3, expressed in terms of the operator t. The kernel of t, of course, is dense in L2 because it contains all smooth functions vanishing at the origin. Now, if you look at the defining equation for the Green's function gz, you should consider this gz as a ket vector on the left-hand side. Then the delta distribution on the right-hand side is a ket vector too, which means that in the definition of t below, the t is not the delta distribution, but it's the adjoint. It's a bra vector, and therefore the adjoint of the delta distribution in the definition of gz. So therefore, the ket vector in the last line, line 7, equation 7, the ket vector defined by the L2 function gz equals the resolvent composed with the adjoint of t on a formal level. I can do that, which in a rigorous more rigorously is the last expression on the last line. T composed with the resolvent and the whole thing adjoint. Now, this new point of view is very important for the following because it can be generalized. It can be generalized to many-body quantum systems. And systematically, the first person to do this was Andrea Pozelikano. Now, he took this point of view and he defined, he built the following theory. So he considered that an arbitrary self-adjoint operator H0 in some arbitrary Hilbert space H, with here we have the requirement the resolvent of H0 should not be the entire real axis, but that's not strictly necessary. Then there is a trace operator called T. We call it trace because it played the role of a trace. The kernel of T should be dense, that's an assumption, and T should be bounded relative to H0. And then we define the operator GZ in terms of the line below. We call it GZ because in the case considered before, it was the Green's function, but now it's an operator from the Hilbert space H to the Hilbert space, which I call X here. Before this X was the set of complex numbers. We define in equation 8 an operator GZ, MZ, in terms of GZ and G lambda. Again, lambda is some fixed reference point. Let's quickly go back that you can compare 8 with the expression in the case before. In line 5, equation 5, you see this inner product of G lambda and GZ and times lambda minus Z. This now has become the operator MZ in equation 8. That's now a bounded operator in the Hilbert space X. So these are the ingredients. And now he defines a class of self-adjoint operators that you can see in equation 9 in terms of this resolvent. And these operators are parametrized by a self-adjoint operator theta. And this theta is an arbitrary self-adjoint operator in the auxiliary Hilbert space X, and just any self-adjoint operator in this Hilbert space X. So we see here in 9 a huge number of self-adjoint extensions of H0 restricted to the kernel of T, parametrized by a self-adjoint operator theta. So this equation looks very similar, this 9 looks very similar as the equation we've seen before on the last transparency, and it's in fact a strict generalization. The theta self-adjoint operator plays now the role of the parameter beta. It parameterizes all the self-adjoint extensions. Again, from the equation 9, we can read off everything that we would like to know about H theta. We can read off the domain, and we see its vector psi belongs to the domain if and only if it is a sum of two pieces, a regular piece called U and a singular piece called GZ applied to W. Now W is not a complex number, but the vector in this auxiliary Hilbert space X. Which in general, the GZW in general will not be in the domain of H0, and therefore the decomposition will be unique. Again, we have a boundary condition, and this boundary condition is the condition that T, the trace operator applied to U, should be equal to theta Z applied to W. Let me once again go back to the previous slide that you can so you can compare. That's exactly the two conditions we had before for domain vectors psi in the case of the delta potential at the origin. Moreover, we can see, and you can see this in the very last line, the action of h theta applied to some vector psi is given by h naught minus z applied to u. Of course, u and w depend on the choice of z, which is a number in the resolvent set of h naught. Any number, by the way, in the resolvent set, if it works for one set, it works for all z in the resolvent set of h naught. Now, this is an extremely general description of self-adjoint extensions of some arbitrary self-adjoint operator restricted to the kernel of some trace operator. And this can be now applied to many-body systems, but it's clear that it will give a far too large class of extensions, many of them being non-physical because not translation invariant or non-local. But from the physics we have in mind, we would like to understand, for example, ultracold gases that we would like to describe by point interactions. We demand that the Hamiltonian should be bounded below. That's number one. And number two, the contact interaction should be of a two-body type. Should not be a three-body, multi-body contact interaction. We are thinking of an idealization of pair potentials of short range. Therefore, the contact interaction should preferably be of two-body type, should be local, and the Hamiltonian should be translation invariant. So there should be translation invariance along the collision planes. Now, this leads to restrictions on this self-adjoint operator theta, which so far was an arbitrary self-adjoint operator. And these restrictions, this mean, for example, this translation invariance means that the theta of z should commute with the total momentum generating translations. So the theta of z should not be any operator. It should be a direct integral, if you like, with respect to the total momentum. It should be a Fourier multiplier that you can see in 10. And theta of z and p should be a function of z minus p squared over 2, p being the total momentum of the pair of particles in the case where you have two particles. And moreover, we have this second equation in line 10. So I'm looking here at two particles at fixed total momentum. And this is basically a one-body system. And the point interaction should be of the same type, should be one of these point interactions that we have met in the case of this Beresin-Fadeev analysis of point interactions at the origin. And the strength of interaction should not depend on the total momentum. And therefore, this f, the function f, should have a parameter beta, but this beta should not be a function of the total momentum. And the other term, which I added here in line 10, is simply the inner product of gz and g lambda that we have that's seen in the slide with the point interaction at the origin. So here gz is not an operator, but it's the Green's function of the free Laplacian. And this condition is called TMS condition for Theo Martirosyan and Skorniakov, who introduced this condition in 1957. Of course, they wrote this condition in a different form. This was much before this Pozelikano's theory, so I've put it in the framework of these self-adjoint extensions as described by Pozelikano. But this is what this TMS condition reduces to in the case of two particles. Now, are there TMS Hamiltonians? Are there Hamiltonians satisfying this condition? It turns out for three particles and more in dimension 3, all TMS Hamiltonians, at least if you have equal particles, TMS Hamiltonians are unbounded below. So this was discovered by Minlos and Fadeev in 1962. That's a very disappointing result. So there are no Hamiltonians which are not bounded below, for example, for 3 bosons with contact interaction in 3 dimensions. If we have, for example, n fermions and one additional particle, which is the so-called Fermi-polaron, and the interaction only takes place between the fermions and the impurity, but not among the fermions, there is no point interaction anyway. So then the TMS Hamiltonian does exist, can be constructed, and it is bounded below for suitable mass ratio. So if the impurity particle is heavy enough, then in fact the TMS Hamiltonian exists as a adjoint operator bounded from below. This was studied by Italians first and finally settled in 3 dimensions by Moser and Schrödinger in 2016. In 2 dimensions, and due to this frustrating news about 3 dimensions, we are now restricting ourselves to 2 dimensions for all, or for most that follows. In 2 dimensions, TMS Hamiltonians do exist, and they were constructed before Pozelikano by Del Antonio figuring theta in 1994, and later by Dimok and Rajiv by a different method. Now, here's the result. And again, I put it into the framework of Pozelikano. In this framework, we start with the free Hamiltonian H naught. All masses are equal to 1. H naught is minus Laplace. Now the trace operator, for the trace operator T, we choose the operator from H2 to the space X, which is a direct sum of these L2 spaces of the collision planes. And T maps psi to the collection of traces. So the Tij are the traces that are introduced in the case of the Lieb linear model. They exist on the space H2. We're not on H1, we're on H2 now, and therefore these trace operators here exist as bounded operators in H2. The kernel of T is dense because it contains the C0 infinity function vanishing on the collision planes. And below here, in the last 2 lines, you see the theta of Z, how it looks, given that it has to satisfy these TMS conditions. And these expressions are, of course, at least the last expression is very specific to 2 dimensions. The fact that we have a logarithm there is a consequence of these 2 dimensions, that the Green's function has a logarithmic divergence, for example, at the origin. Here, by these Greek letters sigma and nu, I label pairs. So in the last line, we see the theta as Fourier multiplier for the pair 1, 2. We have the parameter beta sigma, which measures the strength of the interaction of the pair 1, 2 in this case. And then this function logarithm minus z p squared over 2. P is the total moment, the momentum of the pair. And then we have the sum of the squares of the momenta of the remaining n-2 particles. So this is the TMS Hamiltonian. That's the way it looks like for the particles. Excuse me, for n particles in D equals 2 dimensions. Now, I promised or announced that these operators are limits of Schrödinger operators, and here is the corresponding result again for 2 dimensions. Given a set of parameters, beta, sigma, 1 for each pair, you choose any potential in L1 intersected L2, which is even, and define the Schrödinger operator, H beta epsilon, with 2-body potentials scaled in the way that you can see here. V epsilon is epsilon to the -2, V r over epsilon. Then there is a coupling constant G sigma epsilon, which may depend on the pair, but which must depend on epsilon. And the way it depends on epsilon is given below, as G epsilon has to go to 0, so that 1 over G epsilon grows logarithmically as epsilon goes to 0. And the A sigma, again, sigma is a label for the pair, has to be this integral of the potential divided by 4 pi. It is absolutely necessary for the Hamiltonian H beta epsilon to have in the limit to describe non-trivial contact interactions, and the B sigma describes the strengths of the interaction for this pair. So B sigma is, if you like, another notation for beta sigma. It's a linear function of beta sigma. Then the following theorem is true. If you assume some more decay of the potential at infinity, then H beta epsilon converges to H beta, this TMS Hamiltonian, in norm resolvent sense. Once again, norm resolvent convergence is a very strong form of convergence because it implies convergence of the spectrum, but that's what we want. Since we would like to consider H beta as a model for a Schrödinger operator, and we would like to study the spectrum of H beta, it should have something to do with the spectrum of Schrödinger operator. So this justifies the use of H beta as a model for n particles with short-range interactions. And by the way, we can now restrict these Hamiltonians, all these Hamiltonians, to the subspace of antisymmetric functions, so fermions. And on this subspace, we know there is no point interaction. So on this subspace, H beta reduces to the free Hamiltonian, and the theorem tells us then that the Schrödinger operators converge in norm resolvent sense to the free Laplacian, if you consider it on the fermionic space. And one can derive the rate of, can compute the rate of convergence, and so obtain an estimate on the strength of interaction between fermions with short-range interactions. So this is work in progress that is not yet published. A sort of slightly weaker result, but of the same nature, has been established recently before us, in fact, by Hu, Quastel, and Tsai in a totally different context. It was proved in the context of two-dimensional, of the 2D stochastic heat equation, that we have strong resolvent convergence of the Hamiltonian H beta epsilon for a smaller class of potentials, but nevertheless, same type of result. So this result is also of interest in a totally different context. But this has something to do with the fact that the nth order correlation function of solutions of the stochastic heat equation, if you modify it, so this evolution is then generated by a Schrödinger operator. So once again, you modify the stochastic heat equation, then you have an epsilon and modifying a parameter, look at the nth order correlation function. This is a function of, this correlation function is a function of time, and the evolution of this correlation function is generated by H beta epsilon. This is the connection. Now, I would like to...
Marcel, excuse me, what does it mean? B is some linear function of beta. Is it any function or some?
No, this is very specific. I simply didn't give it. It's some constant plus a multiple of beta sigma. You will understand this on the next slide a little better. Let me
Thank you.
Answer this question later. So I will now come back to this peculiar form of the coupling constant, which I said has to go to 0 in a very special way. Why? How can we understand that? This can already be understood in the case of a single particle in a delta potential, or put differently for two particle system in the center of mass system. So let's consider a two-particle Hamiltonian, and R is the relative coordinate, and let the reduced mass therefore be 1/2. This Hamiltonian, this corresponding Schrödinger operator, rescaled in the form that I've showed you before, with this rescaled potential, and the G epsilon is then given in equation 11. And here you can rescale this operator by putting x equals r divided by epsilon, and then you get 1/epsilon squared in front of this Schrödinger operator, where the potential V is now independent of epsilon, but the G epsilon is still there. Now, due to the 1/epsilon squared in 11, of course, this blows up as epsilon goes to 0. If this operator has negative spectrum, this negative spectrum goes to -infinity as epsilon goes to 0. But if you want norm resolvent convergence, you must have convergence of the spectrum. So you can certainly not have norm resolvent convergence if the spectrum runs off to -infinity. So this means, in order that the operator that you see in 11 has converging spectrum, the coupling constant must go to 0 in such a way that the negative spectrum has a limit. So G epsilon must go to 0. For small values of G epsilon, we have then weak coupling. We are in a weak coupling regime, and the asymptotics of the ground state in this weak coupling regime is well known to be given by equation 12. The ground state energy goes exponentially to 0, like x -2 divided by G epsilon A, and A is essentially the integral of the potential. Now, we want this to behave like we want this to behave like epsilon squared, so that after a multiplication with 1/epsilon squared, it has a limit. If you ask 12 to behave like a multiple of epsilon squared, and then you solve for G epsilon, you immediately get equation 13. And in this equation 13, E is the binding energy. So I assumed that the operator in 11 should have a limit, a negative, should have a bound state energy given by -E, and from this I get 13. -1/G epsilon must have this particular form, with the A being this given constant in terms of the potential. And the coupling strength is measured by this additional constant, which are called B sigma on the previous slide. And you can now understand what this B sigma is here. This B sigma in this two-particle situation is the binding energy, is a multiple of the binding of the square root of the binding energy. Does this answer your question, Jan?
I think so.
Okay. So to conclude my talk, I would like to briefly mention the variational principle that follows from this very general setting, which is always true for these Hamiltonians with contact interaction. So once again, I'm back in the very general setting of Pozelikano. And we have here this variational principle that you can see in equation 15, which derives from the equation 14. And the 14 simply follows from the characterization of the domain of H theta that I have reproduced at the top of this page. And this equation H theta minus Z applied to psi equals H naught minus Z applied to U. Now I put Z equal to some real number E, and then I can compute the inner product psi H theta minus C psi, express it in terms of U and W, and I get equation 14. And from equation 14, you see that if H naught is bounded below by E, for example, if E is negative and H naught is the Laplacian, minus the Laplacian, then you see that the left-hand side is positive, provided H theta is positive, which implies equation 15, or the principle 15. Which is not surprising if we think of theta of epsilon as a Biermann-Schwinger operator. So with the help of this, we can derive lower bounds on the Hamiltonian H, and this has been done a lot in order to analyze n-body systems with contact interactions. First of all, the Hamiltonian H theta, which was constructed by the Antonio figure in theta, was based on 14 and not on the theory that I have presented in this talk. That Antonio figure in theta wrote down the quadratic form 14 and derived the Hamiltonian from this quadratic form, and they used this quadratic form to derive lower bounds. Or other people use this quadratic form then to derive lower bounds for in order to prove stability of the Fermi polaron, for example, in 3 dimensions. This was done by Corecci, Del Antonio, Finco, Theta, Michelangeli, Moser, and Zeiringer. And then it was also done in 2 dimensions later on. Linden and Mitruskas looked at the free coupling limit of the Fermi polaron, so they also looked at the ground state energy and used this variation principle 15 in order to derive a lower bound on H. So this is a very convenient method to do spectral theory, which is a replacement for the fact, or a substitute for the fact, that we do not really have the Hamiltonian. Remember that we have the resolvent of the Hamiltonian, but we do not have an explicit expression for the Hamiltonian. So we have to work with some substitute, and this Biermann-Schwinger operator is the substitute for the Hamiltonian. So with this, I would like to end my talk. Thank you.
Thank you very much. Are there questions for Marcel?
So I have a question, Jan Derezinski. Consider 2-dimensional systems. So you prove that one can approximate contact interactions with smooth potentials.
Yes.
Now, how difficult is this proof? So is the proof for one body or 2 bodies much easier than the one for an arbitrary number of particles, or it's of the same difficulty?
Now, of course, you meet the same difficulties that you have in the case of one particle. You meet again the same difficulties for many particles, but you meet lots of additional difficulties. Unfortunately, already the proof for one particle is fairly complicated. This was done. This is work by Albeverio, Gestesi, Holden, Krohn. You find this in the book Solvable Models that I'm citing here on this last slide. Already this proof is fairly complicated, and it's not a surprise that this is complicated. I mean, you have to, let me go back to the case of the delta potential at the origin, that you can see you have to compute the resolvent of a Schrödinger operator, and you have to show that in the limit you get a rank 1 perturbation. This is not something which is straightforward to get out of a Schrödinger operator. First, you need a formula for the Schrödinger operator, and the formula for the Schrödinger operator, the good formula, is what I showed you here. The Kato-Korula formula. You have to split the potential, write it as a square of the square roots. That's the first line. And then you get this expression in the second line. You have to combine these square roots with the resolvent in the right way. And then you have to show that this has a limit. Now this is, from what you can see on this slide, it's relatively straightforward for one particle. But now if you have many particles, you have to do the same for each pair. And in order to translate this method into the framework for a given pair, you have to go into the corresponding center of mass and relative coordinates. So to do this for many particles involves lots of changes back and forth between coordinate systems. This makes the computation tedious. Maybe it's not technical difficulty, but it makes the computation at least messier. But there are also conceptual difficulties, which I maybe can explain in terms of this side here. The expression on the last line is something which is familiar from the case of one particle. That's the interaction of a pair with itself. In addition, if you have many particles, you have this operator on the second but last line, which is responsible for the interaction between distinct pairs. You have here sigma and nu. They label pairs, but these are distinct pairs. Now we have here a trace operator T sigma, and the GZ nu is a composition of a resolvent and a trace operator. So basically in the mid you have a trace operator, then you have a resolvent, and then you have the adjoint of trace operator. And simply from counting powers, the resolvent is not strong enough to control the singularities that you have here. And you have to show that this operator is bounded. So this is a bounded operator for the case where you have distinct pairs, but not for the case where you have equal pairs. In the case where you have equal pairs, we have the last line. This is an unbounded operator. It's a multiplication operator with an unbounded function. The operator before is a bounded one, but to prove that is fairly a subtle business, because you cannot simply count powers and use Sobolev embedding. You have to do proper cutoffs and so on.
So here two pairs interact with one another. This is
what you see in the resolvent, yes. But
what about a triple interaction? I mean, the three particles can meet. This is not. This is yet a different kind of interaction, is it?
This is inconceivable, of course, but that's not what is described or not what is meant by TMS Hamiltonian. By TMS Hamiltonian, we explicitly mean two-body interaction. On the level of the resolvent, you can then see the interaction among pairs. But in the Hamiltonian, we only have interaction, two-body interaction.
Yeah, yes, but there is a part of the configuration space where three particles meet. And in fact, if particles are three-dimensional, this is the place where the problem appears.
Right. In fact, we need a cutoff there and make a limiting procedure to exclude this.
Oh, okay. So
interaction.
So for two-dimensional particles, you can excluded by the cutoff and okay.
By suitable limiting procedure, yes, so
Yeah.
making a cutoff. This is exactly one of the source of the additional problems that you have with more than two particles. You're right.
Yeah, and what is the additional idea which makes possible the norm resolvent convergence?
Well, the basic idea is what I showed you in the case of the Lieb-Linear model. The basic idea is this Koruno formula. You start with this decomposition. Now the B epsilon is an operator from the Hilbert space into a larger space. It maps into the space of and a direct sum of the L2 spaces over the collision planes. And then we have the expression for the resolvent that you can see down here. And basically, again, you have to show that each of these three operators, you see here a product of three operators, R naught A star, 1 over theta, B R naught. So each of these operators has a limit. And this is the same in 2 dimensions and in 1 dimension, except that in 2 dimensions, in fact, 1 over theta epsilon has a limit and not theta epsilon itself.
Again, next question for Jacobin Wasson.
Okay, can you hear me?
Yes, I can.
Okay, so thank you, Marcel, for a very clear presentation. Maybe just immediate continuation of what Jan was asking. In our paper, Robert and myself on the Haldane pseudopotentials, I suppose you are familiar with or have at least seen that paper. It was published last year, which is delta interactions and derivatives of delta interactions in the lowest lambda level, in the where the free Hamiltonian is a magnetic Hamiltonian. Well, but anyway, concerning this norm resolvent convergence, the way we got that in that setting was simply to look at confinement, so to say, in an external potential. So we had this system confined in, let's say, a quadratic potential, and then the gamma convergence implied norm convergence. So have you considered something similar here, or is that special to the setting we were working in?
Now, as I said, gamma convergence does not imply norm convergence.
No,
resolvent convergence.
No, that's clear. But when you have an external potential, a confining external potential, it does, in fact.
Well, in principle, in the abstract,
not in this.
I disagree.
Not in the abstract framework that
it does
that
not.
you are. No, certainly not. But I'm just saying there is this paper which appeared last year about the Haldane pseudopotentials, and we discuss, of course, exactly the same questions. Well, in a very special setting.
Yeah.
And this issue of strong resolvent convergence and the norm convergence, it arises there.
Yeah.
In fact, also so. Okay, so well, that, the special, of course, in that setting, so is we are reverting in the Hilbert spaces of analytic functions, and there is a very special framework, of course. The free Hamiltonian is the free magnetic Hamiltonian, etc. So it's not exactly the same setting as you are dealing with. But I just wanted to mention this point. But maybe more important, you have a question. Well, it seems to me that you always assume attractive potentials, attractive interactions. Is that?
No, not at all.
No, not the right, no, because well, at least maybe it was just the choice of sign. I mean, on the very first slide, you wrote minus in front of the
Well,
interaction. Of course, the parameter could be negative, then it would be positive, but you...
Yeah. Well, no. Okay, we are mostly interested in the two-dimensional case, I should say. We're not. The one-dimensional case was basically warm-up. In the two-dimensional case, you only have attractive contact interactions. In the two-dimensional case. In the one-dimensional case, you have repulsive and attractive contact interactions. But I mean, this general analysis of Berezin, Fadeev, that you can find in the book of Albeverio et al. Lists all these interactions, and you learn from that in two dimensions, all of these extensions have a bound state. So and that's why basically we consider only, since we are limiting ourselves to a two-dimensional case, we are only looking at attractive potential, but the general setup is does not need that.
Yes, but well, if I may again refer to this paper with Robert.
Yeah.
I mean, we can treat also hardcore interactions and then more general interactions, and we get. In fact, instead of, we do not assume the potentials are that they have a finite integral. So what we get are scattering lengths in plural, because depending on the scalings, we can get the S-wave scattering length or the P-wave scattering length, etc. And these correspond to higher derivatives of the delta interaction. But as I said, that is a special world of itself, the world of the quantum Hall effect. But nevertheless, I think it might be worthwhile to make some comparison, or where are differences and where are similarities. I don't know if you have done that.
No, I have obviously not. I mean, I claim that.
So
I have the delta.
So you have
prime.
not seen that paper.
I have heard talks, but I have not seen the paper yet.
Okay.
Thank you very much for pointing it out to me. I will certainly have a look into that.
Okay, fine. Thanks.
I didn't know that delta primes interactions have significance in physics, physical model.
Yeah, delta double primes even.
Even, I see.
Yeah. Okay.
But once again, there's no assumption about the sign of the contact interaction.
Okay.
For example, here in this first line, you see A star B. If I assumed a positive sign, then I would simply have B equals A. It would make it easier. In this way, the way it is set up, it allows for changing signs, potentially with changing signs even, and you would have then in A the square root of the absolute value, and in B you have in addition the sign of the potential included, like you do it in the analysis of eigenvalues with the help of the Biermann-Schwinger operator. This is all included and allowed in this general setup.
Okay, fine. Thank you.
Thank you. Are there further questions? A question?
If I may say, add something to respond to Jan's question. When you prove existence of this limit that you can actually, of this resolvent that you can see, an important idea is to split the theta epsilon of Z into a bounded and an unbounded part, so which corresponds here in the case to the diagonal part and the off-diagonal part, where diagonal refers to these distinct or equal pairs. So this splitting of the theta epsilon plays an important role, because there is the coupling constant, as I showed you, which goes to 0. And this coupling constant emerges here in the inverse. So you get 1 over the coupling constant, and this goes to infinity, and it has to compensate an infinite operator which occurs here in the theta of epsilon.
Mhm.
This is similar to the one-body case, but in addition, you have to do the splitting between the bounded and the unbounded parts to actually properly isolate the divergent part from the non-diverging part.
Is this splitting epsilon dependent? Or
No, this is not epsilon dependent. I don't see how it is now. No, in a way, if you look at this as a model of renormalization, and I've showed you the running coupling constant, you can consider this as a model of renormalization. And in fact, there is a whole community in physics who play with these models as toy models of renormalization. Then it's a very simple toy model. You have basically a one-step renormalization that takes place. This is nicely described in the paper of Timok and Rajiv, who write down this analysis in a second quantized language. And then in terms of normal ordering, which occurs here in this Spearman-Schwing operator, they can nicely isolate the divergent part, which is then cancelled by the 1 over epsilon, 1 over g, by the inverse of the coupling constant. And that problem is then solved.
Of course, if dimension is 2.
If dimension is 2, right.
I actually wanted to ask about dimension 3. I mean, we all know that the Hamiltonian is not bounded from below. I mean, but still it exists. I mean, there are self-adjoint extensions.
Certainly, right.
So
Yes.
one could ask the same question. Suppose you have a family of, I mean, of scaled two-body potentials with some running coupling constants, and shouldn't you have some kind of convergence to one of these self-adjoint extensions, which will not be bounded from below, but to bed?
That's a good conjecture. But I assume, I mean, this fact that the operator is unbounded below, this will lead to problems in the proof.
You cannot use form.
No. I mean
techniques, but
no, I mean something else. Let me explain. I showed you this variational principle, right? This variational principle 15. And you already have this variational principle on the level of the approximating Schrödinger operators. Okay? And the fact that the Hamiltonian is not bounded below, I mean, this arrow is in 15, this implication goes in both directions, at least on the approximating level. Goes in both directions. The Hamiltonian is unbounded from below in the limit, and which it is for 3 particles, 3 dimensions, then the theta will be unbounded from below. And this implies problem in controlling the resolving convergence. Because we actually work with this boundedness. It's one of the ingredients to prove, sorry for jumping back and forth, but here you see it again, in order to control the convergence of the 1 over theta epsilon. we need to split it into two parts, bounded and the unbounded. We control, we proved invertibility by showing that the diagonal part can control the off-diagonal part in the sense that the inverse of the diagonal part times the off-diagonal part becomes less than 1. But we need to have the inverse of the diagonal part of the Hamiltonian, and therefore we must have control over the spectrum of this diagonal part. And if it's unbounded below, we have no control of the spectrum. So we must have control in order to work with this here, 1 over theta of epsilon, proving convergence. We must have control over the spectrum. And essentially, this requires us to have a lower bound of the theta epsilon, which implicitly then means that the H must have a lower bound. So there is a principal problem here. But I'm not saying it cannot be overcome, but we have not succeeded. We have not seen yet. We have thought about that. We have not seen how to overcome this problem.
And there is a good reason why you cannot go to complex Z.
You can, but of course you can.
Well, you have to.
Sure, you have to. Yeah, still you. Well, I would have to think about that once again, but of course we did consider that. I mean, we did consider this point.
Thank you. Further questions? No further questions. Thank you very much, Marcel.